Okay, let's continue our discussion. So here we have example 10.7. An iron bar and a brass bar are soldered end to end as shown in this figure. The free ends of the iron bar, this one is one free end for the iron bar and another for the brass bar. So these two are maintained at 373 Kelvin and 273 Kelvin. Okay, so every units are in SI system, so no need to worry about unit conversion. Okay, let's go on. Obtain expression for and hence compute the temperature of the junction of the two bars, that is temperature in this region, and the equivalent thermal conductivity of the compound bar, that is the system made up of these two, and then the heat current through the compound bar. Okay, so once it attains steady state, the heat current through this system comprising these two bars, let's say the heat current is H. And as we know that this H is proportional to, experimentally we have already discussed about these things. So experimentally, the heat current will be directly proportional to the temperature difference. Look, this is at higher temperature, this India's lower temperature. So the heat current will be from this end to this end. So this is proportional to temperature difference. So here T1 minus T2 and directly proportional to the cross-sectional area. So let's say this area is A and length from here to here inversely proportional of this length L. And we know if we replace this proportionality sign with equality sign, there will be a constant, proportionality constant, that is thermal conductivity here, and then we can write T1 minus T2 divided by L. Now, what about these two bars individually? So for iron bar, let's say the heat current is H1 and this will be K1, A1 and T1 minus, look up to here it is, so T1 minus T naught divided by L1. And for brass bar, let's say heat current is S2, so K2, A2, and then look, this is at higher temperature, which is T naught. So T naught minus T2 divided by length of this brass bar. Now, we have to obtain expression for the temperature of the junction of the two bars. Means we have to obtain what is T naught here. Look, one thing here, L1 and L2, these two lengths are equal. Means these two bars are identical in length and as well as in cross-sectional area also. But as they are made up of different materials, so conductivity, thermal conductivity is different for these two. So we can write this A1 and A2, L1, L2, these two are equal. So no need to worry. Now, what is the main thing here? In a steady state, this H heat current across this complete system or this compound bar, you can say, will be equal to this H1 and H2, not the sum. All these three things are equal. That is, heat current, overall heat current should be equal to the heat current through the iron bar should be equal to the heat current through brass bar. Steady state we are talking about. Means there will be a continuous heat flow. Okay. So if we are taking this thing into picture, that is H1 equals to H2, we can write H1 equals to H2. Look, I'm going to obtain T naught. So H1 equals to H2, that is K1 into A1 into T1 minus T naught divided by L1 should be equal to K2 A2 T naught minus T2 divided by L2. And we know A1 equals to A2 and L1 equals to L2. So this will be simplified to a new extent. K1 T1 minus T naught equals to A2 T naught minus T2. Now we can write K1 T1 minus K1 T naught equals to K2 T naught minus K2 T2. And then we can write, look, what we can do, we can bring this thing this side, or we can simply add K2 T2 both sides. So we have here K1 T1 plus K2 T2 minus K1 T naught. I'm just adding this term both sides. So here we will have K2 T naught plus K1 T naught. You can do it by yourself. This is easy one. So here we have K1 T1 plus K2 T2 divided by K2 plus K1. Okay, I'm writing it directly because once we take T naught common here, there will be K2 plus K1 as factor, and then we can transpose that thing to this part. So you can try by yourself this calculation part and you can arrive at this situation. So we have here T naught, that is the temperature of the junction, and everything is given here. So we have here K1, T1, K2, T2. All things are here. K1 is given, K2 is given, T1 and T2. All things are here. So we can do one thing. We can put all these values and then we can compute for T naught. And I am leaving this part to you. You can just put all these values here and then you can obtain this T naught, and it should be somewhere 350 Kelvin, and it will be in SI system also because everything is given in SI system. Okay, now moving to the second part, uh, the equivalent thermal conductivity of the compound bar. Again, we are going to use this fact. This is steady state. So let's take H equals to H1, one part from there. So what we can write here for the second case, let's write H equals to H1. H is nothing but K times A times T1 minus T2, as we have discussed earlier, divided by length of the system or the compound bar. And then here we have K1 A1 T1 minus T naught divided by L1. And we know L1 and L2, these two terms are equal, means these two lengths are equal here. Look, L1 is given 0.1 meter, L2 is 0.1 meter, and L is nothing but the sum of these two. So we can write L is nothing but 2L1. So in the next stage, we can write K A, and cross-sectional area will be the same. So this will be equal to A1 only. T1 minus T2 divided by twice of L1 equals to K1 A1 T1 minus T naught divided by L1. And it will be simplified. K T1 minus T2 divided by 2 will be equal to K1 T1 minus T naught. And instead of T naught, we can write this expression here. So let me write it. This will be K1 T1 plus K2 T2 divided by K1 plus K2. And then we can write K1 into, look, here we have K1 plus K2, K1 plus K2. And then here we have T1 into K1 and T1 into K2. So T1 into K1 plus T1 into K2. Okay, we have to write this thing also. So let me create some more space here. Here we will have K1 into T1 and minus K2 into T2. Then K1 T1 is here and K1 T1 is here with negative sign. So these two terms will be eliminated with each other. And then we will have here T1 K2 and here T2 K2. So we can take K2 common outside. So here we will have K1 into K2 multiplied with T1 and here minus T2. So T1 minus T2. You should try by yourself these all steps, and then if you are finding anything not good, you can try again, and ultimately you will reach here. So what is happening now? We have expression here K times T1 minus T2 divided by 2 equals to this much, and you can easily see here T1 minus T2 is common both sides, and here we have divided by 2. We can multiply both sides with 2, and then we will have this equivalent thermal conductivity twice K1 into K2 by K1 plus K2. So this is expression for equivalent thermal conductivity. Means if we are taking these two rods combined, as a system, what should be the thermal conductivity of this system in terms of the individual thermal conductivities of these two rods. So this I have written here, and now you can put the values for K1 and K2, and you can obtain what is the value of K. 91.6 watt per meter per Kelvin. So this is in SI system only. Okay, now moving to the third part of this question. We have to obtain the heat current through the compound bar. So we have already obtained this thing here. So heat current through the compound bar will be the thermal conductivity of the compound bar into its area into the temperature difference of the two ends divided by length of this compound bar. And we have all these things. So you can put K as we have just obtained the value of K here. So you can put the value of K here, and area, cross sectional area will be the same. So any one of these two you can take because these two are equal, and this is the cross sectional area for the compound bar also. So you can put this value here. T1 is given, T2 is also given here, and L is the complete length from here to here. That will be twice of the length of individual rod. So this will be twice of 0.1 meter. That will be 0.2 meter. So after putting all these values, you can obtain what is the value of this heat current is. And it should be somewhere 916.1. I have taken this value from your textbook only. Watt or joule per second, you can say. So this is all for this video.